34 thousandths. You have got to be kidding me. Every time I let my guard down for 1 second, this project kicks my ass. Hello Internet, my name is Quinn, and this is Blondihacks. I'm back on the big steam engine today, and we're going to make a part that's always exciting on a steam engine, and that's the cylinder casting. Now, once again, the challenge on this engine is the size of everything, so if you've been wanting to see sketchy faceplate setups, well, buckle up and let's go. Here's the casting for the cylinder. It's really quite lovely. I'm consistently impressed with the castings in these PM Research kits. This is really very nice. What I love about this one is that the steam passages are cast right in there. You can see that they've done cores in the casting so that you don't have to drill out or machine out those passages. Really cool. It's very intricate foundry work there. Quite impressed. All right, I'll start by fettling it as usual with my Dremel, getting rid of all of the flashing and such on all of the seam lines and so on where the cope and the drag meet. And I decided to get out the big guns here a little bit and hit the ends with the flap wheel. And then I'm also cleaning out those cast-in passages to make sure that there's no sand or anything else blocking those up. I'll take some quick measurements here just to see how much material I have to remove. That'll help me decide how to go about doing this, and there is a lot to remove, which is good. Gives me options here. Now, I think I'm going to do this on the faceplate. It's going to be a hefty boring operation, so I think the lathe is the only way I've got to really do this. I'm mocking up some clamps here for how I think I might want to hold this. Then I'll transfer punch those, and I'll drill and tap the faceplate here for mounting bolts in those locations. I'm just making sure that they're equally spaced between the lines there. Might as well, not that it really matters. One of the best pieces of advice I got for the faceplate was actually from a viewer who advised me to stop treating my faceplate like some sort of sacred artifact and just drill and tap holes wherever you need to for mounting things on it. I was struggling a lot to use those clunky factory slots there for mounting smaller parts, and that was good advice. Once you get over the fear of putting holes in your tooling, it really does speed things up and makes things a lot easier. It's a faceplate, just modify it, that's what they're for. Tappy tap tap. So after drilling and tapping, I got out the precision ground flat stones and just gave the face a little stoning here, make sure there's no burrs or anything from those operations. Everything looks really good there, nice and flat. At this point, I realized I was going to need a reasonably flat starting surface to start the machining on, so I got out the angle grinder and did my best to kind of create a flattish surface on one end. There's quite a lot of draft angle on the ends of these parts, and it's very, very wobbly, so I really need to get it closer to flat before I can even start. So I'm just hitting it with the grinder and checking it with a scale here by eye and just removing the worst of the high spots. If we can't get it to sit reasonably flat, it'll be difficult to clamp it securely to the faceplate, so that's why I'm starting here. And there's so much material to remove that I don't have to worry about doing this. Now it sits flat, but of course it may not be sitting vertically, so we'll get to that here in a sec. But I've got these specialty faceplate clamps that I actually just made. There will be a video on these. The design of these is such that all the components of them are captive. There's nothing held in by friction alone, so I don't have to worry about things flying off when the faceplate spins up. Now I can get out the square, and I'm going to get the casting squared up to the faceplate. Of course, I'm using shims for that, so you might ask, well, what was the point of grinding that flat if I'm going to have to shim it anyway? And what that did was minimize the number of shims. I only have a couple of shims instead of like a whole pile of shims under there, so it'll be a more secure clamp. And then I'll throw some tape on there to at least reduce the velocity of those shims as they fly off the faceplate into my pie hole. I had centered it up roughly with a scale, and so let's get the faceplate mounted up and see how well it's running. It should be at least in the ballpark here. And that actually looks pretty good. Of course, it's running very eccentrically. There's a lot of offset mass from the valve body there, but we'll deal with that here next. So I've got some counterweights here to mount opposite the valve body. This is an old school trick. Your change gears are an easy source of boltable counterweights. So I'll put a couple of those on there and see how that runs. That's better, but it's still shaking the lathe around quite a bit, so I'll do a little more here. The other thing I will use is these pieces of lead. This is just lead sheet that you can buy and roll, and I just cut little plates and drill holes in them, and then I can bolt those onto the faceplate. That gives me an easily adjustable counterweight for setups like this. So I went up and down a bit with the counterweights until I got it to where the lathe was running reasonably smoothly up to 400 RPM, which is more RPM than I will need, so I feel good about that. I only need to run this at about 250. Now the hard part, getting this thing dialed in. What I decided to do was mark some reference points around the cylinder body there. I don't have full access to 360 degrees, of course, and there's model number markings and flashing and other areas on the casting that I can't use for indicating. So what I did is I marked 4 or 5 places where the bore of the cylinder is unmolested and will make a decent reference. And then I went back and forth mark to mark and tapped it in, reducing the run out as much as I can amongst all of those marks, if that makes sense. So as I rotate it, you see the indicator swinging all around, but that's because it's passing over the invalid areas of the casting until I get to the next mark where it's a valid reading. And so doing this, I was able to get it to within about 10 thousandths, which was pretty good for, a rough casting like this. I can also check it on the flange out here, but of course on the flange I only have 180 degrees of travel before you get into the valve body and the reading becomes invalid. On the main body of the cylinder I had a little more than 180 degrees to use. Then I also double checked it vertically here, and this actually looks really good. I'm within a couple of thousandths of square to the lathe there. So the bore should go straight through the casting, which is good. I'll do one last check on all my clamps there, make sure everything's tight. I had to loosen the clamps a little bit here and there as I was tapping to get the thing to move. It looks like it's running well. You can see the cast bore there is running reasonably true for a cast bore. Feeling pretty good. In order to get some ballpark for how much to remove from each side so that the casting ends up centered when I'm done, I'm going to use this boss here as a reference. This is the steam port. So I'm using a center finding tool here to get a decent estimate of the center of that cast boss. It's always difficult to get the center of something cast like this, but this should get me pretty close, I hope. And then I used dividers set to half the length of the final cylinder and scribed a line at each end from that center line. That'll tell me when I'm close to final depth on each end. One more trick I can do to verify concentricity is I can blue up the end here, and then what I did was I took a turning tool and I used it to scribe some dashes around the outside here by hand. I'm not doing this under power because the surface of this casting is so uneven that I can't take a continuous cut on it without going really deep. So I'm just manipulating it by hand here and making a little dotted line, and then I can visually see if that dotted ring is concentric with the outer edge of the casting. And if so, then my bore is going to end up looking nice when we're done. And that actually looks really good, so I feel confident, and we can start making some chips. I'm going to start by facing the end here, and I'm spinning it up gradually here, and it's going to be a very long interrupted cut for a very long time. Operations like this are always kind of tedious because it's effectively a very large diameter facing cut. You have to face all the way from the edge of the valve body to near the center of the bore, but for most of that time you're cutting air, so it just seems like nothing's happening. You're just running the lathe for, an hour solid and seemingly nothing's happening. But the deeper we get, you can see where I've knocked off all the high spots there, and we're starting to make progress, and eventually we get into some full cut. Once you get into the center here on a full cut, it's very satisfying. Now we're moving some cast iron. So far so good. I'm about halfway to my mark there, and the finish is really good, so I just proceeded like this. The slow-mo cam really shows off the clamping system there that I built for this, and it's doing its job very well, I have to say. It's really holding up extremely well. Since this is the first side, I just machined it down to my layout mark there, and that looks like we're there. So now the other end will be machined down to the final accurate dimension. Finish on that looks great. I'm really pleased with how that went, so I think it's time to move on. Now I'm going to do the big boring job. My weapon of choice for this is the Shrum Solutions 16mm solid carbide boring bar. It's the largest boring bar that I could get on short notice and at a reasonable cost, so this is what I'm going to try to use for this. A thicker boring bar would be better because you can see how much stick out I'm going to need here. You can go as high as a 1-inch boring bar on an AXA tool post like this, but I don't have a 1-inch boring bar or the appropriate holder for that, both of which are quite expensive. I considered making a boring bar for this, which would have been a pretty easy project, but since this really nice solid carbide boring bar was on hand, I thought I'll try this first and see how it goes. The rule of thumb for boring bars is that you don't want to go farther than 6 times their diameter on stick out. So this is 6.5 times. I'm definitely pushing it here, but this being a solid carbide bar and I'm taking light cuts, I can push the limit a little bit. And honestly, this is working really well. I'm asking quite a bit of this bar and it's performing like a champ, I gotta say. The first couple of passes were very light, just feeding by hand because I wanted to feel out the inside of that bore. Because it's a casting, I don't know, there might be taper in there might be weird high spots, there might be chunks of flashing or who knows what might be in there. So I go in by hand a little bit, knock the high spots off, and then I start power feeding just so there's no surprises once the lathe takes over. But from here, it was just a whole lot of passes. We had a lot of material to remove. They give you a lot on this casting, which is nice. I should be about 2/3 of the way there now, so I'll check my diameter here with the bore gauge. And things are looking good there. So while I'm at it, I'm also going to check for taper. If there's any taper forming in this bore, I'd like to know now so I can go and check the back of this bore as well. And the good news on this front is that I've got less than a couple of tenths of taper, so very happy with that. That's looking really good. This boring bar is doing a top-notch job. Before I get too close to the end, I'm experimenting with different speeds and feeds and depths of cut and things to find out what works and what doesn't for this particular setup and this particular material and cutter. And that's really important because, for example, with this boring bar, as is often the case with carbide boring bars, it does a lot better with heavier cuts than lighter ones. Lighter cuts will chatter, whereas a heavier one won't. And that's information you want now before you get too close to your final dimension, because if you get to the end and you have to do a 5 thou pass to finish it up and you find out you can't without chattering, well, now you're in big trouble. Now in my case, I did end up having to do a lighter cut than I wanted to for the end, but here's a trick for holding chatter at bay for a single pass like this. Just fiddle with the speed control on the motor. That little bit of acceleration and deceleration of the spindle prevents a standing wave from forming, and you can hold chatter off for a while like that. I think some high-end CNC machines actually have this built into the computer as a feature. They can randomly vary the spindle RPM within 100 RPM range, something like that, to reduce chatter. Furthermore, because I've learned I can't take light cuts, I'm not doing spring passes, which I normally would with boring. And when I'm done, of course, I'm careful to wind the bar clear of the work so I don't scratch it up on the way back because I know that bar has deflected. All right, final dimension check. This is an important one. Got to be 0 under to 2 thou over, and I am 1 thou over, right in the middle of the tolerance. I will take that. Metric horns of victory. Now, what about taper? That's also very important. There needs to be minimal taper in a bore like this for a piston to run in it. And we are within a couple of tenths of no taper. Double metric horns of victory. Since it's the same bore as the crosshead used, I can slide my engine alignment bar that I made in here. This will be a useful reference for setting up this engine later on. And that's a really excellent fit in there. All right, I'll break that edge now. I'm not going to chamfer that because we want a good close fit with the boss on the cylinder heads there, but I do want to break that sharp edge. Now I can pull the faceplate off. It's easier to do this on the bench, and pull the part off, clean everything up, deburr it, flip it over, and mount it back the other way. I marked the faceplate there for where the valve body goes to make sure I get my counterweighting about the same. And I was able to clamp it up, set it up again, and face the other side. The lathe is wobbling here a bit. I didn't get the weight balance quite as good the second time around, but that's okay, we're just facing. And I gotta tell you, on this whole project, power crossfeed was the hero, because boy, this would have been tedious if I had to do all of this crossfeeding by hand. There was a lot of material to remove, a lot of passes, and just being able to set it up and keep an eye on it sure is nice. And now for the bad news. I was keeping an eye on my progress here with the depth micrometer down to the faceplate there to get the final length correct, and well, I actually ended up blowing that dimension by about 34 thou. Now, let's look at how that happened, because it's an exercise in understanding yourself. The dimension is specified in the drawing as 3.38, And I have some sort of weird small case number dyslexia where when I look at a number that way, I see 3.038. As I was closing in on that dimension, I was doing the math with a calculator, no less, multiple times over and over and over again. And I was making the same mistakes over and over and over again. I was calculating to 3.038 and not 3.380 every single time. So even though I was checking over and over, I was continuously making the same mistake in my head, and I ended up passing the dimension. Now my layout marks that I'd made earlier actually saved me because I realized something was wrong because I hit my layout mark way sooner than I thought I should. And that's when my brain finally did the right thing and I realized I was under. The good news is this error isn't that serious and it's easy to correct for. The dimension actually has a 10 thou tolerance on it, so including that, I'm actually only 24 thou under. So that's 12 thou on each face. And that's actually easily compensated for by thicker gaskets, or I can remove a little bit of material from each side of the piston so that the steam expansion zones end up the same size. But honestly, I could also probably do nothing and the engine would run just fine. It's not enough of a difference to be a huge concern, but we'll cross that bridge when we get to the piston. The takeaway here then is if you can understand your own cognitive weaknesses, it really helps you prevent errors. In my case, knowing this about myself struggling with number transposition like that, I do layout marks and other double checks a lot, as you see on my channel. And in this case, that layout line kept me from scrapping this part entirely. Over to the mill now, I'm going to set up to do the valve body. I wanted to do this on the mill if possible because I'm going to need to ream it and it's going to be easier to get the position of the two bores correct, I think, on the mill. So I've got it set up here with my coaxial indicator and I'm centering the main bore on the spindle of the machine. Then I translate over the specified distance between the bores. And I've got a gauge pin in the spindle there and I'm attempting to line the rough cast bore for the valve on that pin. I'm doing this by tapping it into position while using my finger as a fulcrum on the back so that the casting rotates more than it slides. And once I've got that valve body lined up, then I go back to the main bore, check the runout on that, and of course it's off a little bit because the casting moved a little bit. So I dial that back in and then I go back to the valve body, tap that in again, and go back and forth until both are aligned. You get a little closer to both bores being in the right position each time you do this. This was a little tedious, and I actually did come up with a better method here later, so stay tuned. But now I can come back in with a drill. Luckily this is a reduced shank drill, which will fit in a collet because I don't have clearance here for the drill chuck, and I'm able to drill this out the pilot drill size for the reamer that I'm going to be using in this. Because it's a small diameter and quite deep, I don't think a small boring bar would be a possibility here, so I think a reamer is really the only way to do this feature. Unfortunately, I don't have the quill travel for a hole this deep, so I had to drill the hole halfway down, then lower the head, and then finish drilling the hole. The secret weapon for this feature is this beast of a reamer. This is a 5/8 reamer that I had to buy special for this operation. Actually, the funds for this were donated to the channel, so thank you very much to my awesome viewers who make projects like this possible. And the secret sauce here is that this reamer happens to have a shank on it that will fit in a collet. This is what made it possible to do this whole thing on the mill for me because I just don't have the clearance normally for big reamers like this. Luckily, a reamer in this size exists with a standard collet-sized shank. Otherwise, I was going to have to do this on the faceplate again, and that was going to be more difficult to set up to get the bores the correct distance apart and such. But once again, I did have limited quill travel here, so I did have to do this hole in 2 stages. I just kept the reamer running, lowered the head, and then continued with the quill, and then lifted the head back out, and then retracted again. A cool thing about this setup though is that I can get another important feature done while I'm here. And that's the first of the bolt holes for the mounting of this cylinder. The alignment of this hole in particular is crucial because it has to be on the same axis as the 2 bores. So since I have the bores aligned to the x-axis of the mill now, I can do this. Now the drawing actually specifies that this hole is supposed to go all the way through into the steam channel because there isn't really room otherwise. I didn't love that, and I actually tried to stop short of doing that because I think there is enough depth. But unfortunately, I went a little too deep and I broke through a little bit. But that's okay, it's no worse than the drawing says it's supposed to be, and we'll have to put thread sealant on that particular bolt. That reamer did a really nice job in there. You can see the finish in there is great. It's notoriously difficult to show surface finishes on camera, but hopefully you get the idea. You can see there that there's, of course, cross holes in there for the steam passages, which is why I specifically chose a spiral flute reamer for this. Spiral flute reamers are much less likely to hang up when there's any kind of side intrusions in the bore, especially longitudinal features like keyways, but they're better in a case like this as well. But now you can see why I needed that first hole. I could put my drill template that I made all the way back in the first part of this series and use a gauge pin to align to that first hole that we made, and that gets the drill template aligned correctly for the overall orientation of the engine. And this is crucial because, well, A, remember this is a weird bolt pattern, it's not a standard one, and B, this makes sure that the valve body is correctly aligned with the crankshaft so that when the eccentric is on there, the valve rod is going to come up in the correct place on the valve body. I did the frame on the drill press for this, and I could have done that here as well, but the mill was just as easy. Even though I have the DRO here on the mill, this saved me having to do the math and trying to get everything aligned. I'll set this up horizontally now and clamp on those two parallel faces. I'll put some packing under there, and I'm getting the casting level using these two bolt holes. If there's roughly the same amount of each hole visible above the vice jaw, then the casting is roughly horizontal. Close enough for this. I'm just drilling this boss out here for the steam port. I had already marked the center of that previously, as you saw, for getting the layout for the end faces. So I used those same marks to center my drilling up here for tapping the threads for this fitting. Now, unfortunately, I did not get this very centered, as you'll see. I seem to be really terrible at getting holes centered on bosses, but anyway, this is specified as a 1/8 NPT thread in the drawing, so that's what I did. I am on record as strongly disliking pipe taps, and that has not changed. I don't know how you're supposed to figure out how deep to go with those things. I always end up just trial and erroring it with a test plug like this, and if it looks like I've got lots of threads engaged and it gets tight as you tighten down the tapered thread, then I figure it's good enough, but yeah, I don't like pipe taps. And then while I'm here, I'm also going to face off this surface here. There will be a plumbing fitting seating down on this, so it's nice if there's a machined face for it to seat down on. And then of course there may be a burr on the back side of that hole, so I just run the reamer down by hand to clean that out. And note that I'm always turning the reamer forward no matter what direction I'm pulling on the reamer. Resist the urge to untwist it as you pull it out, because you can actually dull the reamer doing that. For the bolt hole pattern on the other side, I had a better idea for how to set it up. I put it on the rotary table. I wish I'd had this idea before, because this is a much easier way to do it. I start by centering up that main bore again by tapping it in, and that's not too difficult. And now I can just translate over again the distance between the bores, and I just rotate the rotary table until it aligns with the pin. And I can also adjust the x-axis only if I need to, because the distance between the bores might not be perfect. That's not a critical dimension, so I may not have gotten it perfect when I first drilled that. And so a combination of manipulating the x and manipulating the rotation gets the two bores on the x-axis of the milling machine. And this is much, much quicker because adjusting the rotary table does not affect the alignment of the main bore on the 0 position of the spindle. And then I can lock the rotary table. And the cool thing is now the DRO knows where both the center lines of those bores are. So I can do the bolt pattern here, and then I can do the bolt pattern on the valve body as well. You might be asking, why am I using the DRO here for this bolt pattern instead of using the rotary table that it's sitting on? Rotary tables are a perfectly valid way to do bolt patterns. The reason is simple. I'm near the end of a complicated and expensive casting, and now is not the time to experiment with new techniques. I do not have a lot of experience doing bolt circles with a rotary table, but I've done a lot of them with the DRO. So I just use the DRO because I know that's going to work. Now I have a lot of tapping to do, and all the setups that you saw here were tall, so I didn't have room to do the tapping in the mill. So I put together a field expedient tapping guide here. This is just a squared up block with some close fitting clearance holes for the taps. I clamp this to the surfaces lightly with a toolmaker's clamp. The idea is that you want the block to be able to move so that the taper on the tap centers it on the hole, and the block is just holding the tap square to the surface. This actually works really well. I left extra space there on that block because I'll put this in the drawer when I'm done, and I'll add holes to this in the future as I need them. A tapping guide is a very useful thing that I'm surprised I've made it this long in my life without having one. Back to the mill with these set up the other way here now on the side, and I'm going to drill and tap for the drain cocks. My previous engine didn't have these, but this is quite a bit larger engine, so it really does need them. Cylinder drains are opened when you first start the engine because the cylinder is cold, and so the steam hitting it condenses into water, and you need somewhere for the piston to be able to push that water out of the cylinder so you don't hydrolock it. You've seen locomotives starting up at the station, and there's steam and water pouring out of the bottoms of the cylinders. That's actually the drain cocks that you're seeing. Once the locomotive is running under speed, those drains are closed, and you don't actually see much for steam coming out of the engine anywhere. I also spot faced these, as you see here, so that the nut on the valve has somewhere to sit down and you can get access to that nut with a wrench. Once again, the back of those holes probably has a burr which could interfere with the cylinder, so I'm using this Noga backside deburring tool to get to those. You can see how it sits kind of in the middle of where the steam expansion area will be, so when the piston is pushing the old steam out of this end of it, if there's water in there, it's going to push it right out that hole instead of jamming up on the piston and hydrolocking it, which can potentially damage things. Smaller engines get by with just pushing the water past the rings, which works okay, it's just kind of messy. Okay, let's sit this thing on the engine and see what it looks like. Boy, look at that. You can see this thing is up to 18 inches now in height, and we're not done yet. There's more parts going on top of that. But so far, looking pretty good. You can see how the alignment bar here is really going to help me when I go to set up this engine in the end. Because both bores are the same on the crosshead and the cylinder, I can get everything nicely aligned here. Well, there's my final casting, and I'm really pleased with it, aside from the annoyingly off-center steam port, which is going to be covered with plumbing anyway, so I don't think you'll notice. But there was a lot of tricky operations on this, and everything honestly went really well, all things considered, so I'm very pleased with this part. Can't wait to get it on the engine. Thank you very much for watching. I hope you found this interesting and useful, and thanks to my patrons especially who make all of this possible, and I will see you next time.